Okay, I've got a new problem up here. I want to find the surface area of the sphere of radius A. So I'm not specifying what the radius is. We're basically going to do infinitely many problems all at once. For an arbitrary radius, we'll find what the formula for the surface area is. Now, by saying that that's the radius, though, I am specifying that A is a positive number. In theory, I could have a degenerate sphere of radius 0. I think pretty obviously that's going to have no surface area. Okay? So for a non-degenerate sphere, the radius, by definition, must be positive. All right, now I'm going to suggest that you folks pause the video and try to get this on your own, but I'm going to warn you it's a long problem. So I'm going to just suggest several points at which you might want to just tune back in and check your work. So the first thing I'm going to need to do is write down the parametrization. So I will need to parameterize my sphere. Once I've done that, I'm going to need to calculate del R. I'm just going to write del U and del R, del V, although I'm going to tell you that I'm probably going to call my parameters by different names, because remember, the sphere I could view as a constant row surface in spherical coordinates, so I might choose in step 1 to parameterize using theta and phi. In fact, I guess I've just given that away. So I'll be calculating del R, del theta, and del R, del phi. Okay? Then, once I have those, I'll calculate their cross product. And here, the order in which you do that really doesn't matter. There will be times that I care about the direction of this vector, but in this section, we're using this cross product in 2 ways. We used it in calculating the tangent plane, because this is going to be normal to the tangent plane. But when I'm calculating a tangent plane, this is my plane. I don't care whether I use a normal vector that points that way or that way, as long as it's normal to the plane. And for the purposes of surface area, of course, what we're going to do as soon as we calculate that is we're going to calculate its magnitude. And so if you did this in the opposite order, you'd get the opposite vector here, but you'll get exactly the same magnitude. Okay. And then in step 5, we will integrate. So we'll be taking the double integral over d of the magnitude of del R, del theta, crossed with del R, del phi, dA. That does mean part of writing my parametrization is figuring out how I want to restrict the parameters to define this region D. So in the last example that we did, we were working with a cone, and we were just working with a part of a cone. If we hadn't restricted our R values to be between 0 and 2, it was the cone Z equals R. If we hadn't restricted R to be between 0 and 2, we would have continued the cone up too high and gotten part of the cone that we didn't care about. And if we hadn't restricted theta to be between 0 and 2 pi, we would have gotten multiple copies of the cone. So anytime you're writing your parametrization, part of that is also restricting the domain of that parametrization, because otherwise you're implying that you're letting theta and phi, in this case, go from negative infinity to infinity, and that's not what we want. Okay, so restricting the domain so there's not just the natural domain of your functions is part of writing the parametrization. Okay, so with that said, I would encourage you to pause the video and try to work this through. Feel free after any of these steps, if you want to tune back in to just check your work and make sure we're on the same page, to go ahead and do that. All right, so if I'm parametrizing this, as I said, I'm going to just use spherical coordinates. So I know that in general, x is rho sine phi cosine theta. And if my radius of the sphere is a, that just means I'm replacing rho with a constant value of a. So I'm getting a sine phi cosine theta for x. Y, in general, is rho sine phi sine theta. So that just becomes a sine phi sine theta. Z is rho cosine phi. So that becomes a cosine phi. And if I want to get the sphere once, and I'm thinking of this as spherical coordinates, well, in spherical coordinates, phi is restricted anyway, so that it only takes on values between 0 and pi. And I definitely want it to take on all of those values, because 0 would be pointing straight up, pi would be pointing straight down, and so that's what's going to sweep out the entire sphere. Theta, in general, isn't restricted in spherical coordinates, but if I want to get this just once, I only want to work with theta being between 0 and 2 pi. Okay. So, I could write my parameterization as r of theta phi equaling a sine phi cosine theta, a sine phi sine theta, a cosine of phi. And I'm restricting my domain so that phi is between 0 and pi, and theta is between 0 and 2 pi. Now what that means is that in the theta phi plane, the region over which we're integrating will be this rectangle. So theta and phi in my parameter plane are just rectangular coordinates. Once I apply the transformation so that we're in 3 space, they will take on their role as spherical coordinates. Okay, excellent. So there's our parameterization. So now let's calculate our partial derivatives and get the cross product. So the partial of r with respect to theta, let's see, that's just going to be negative a sine phi sine theta, a sine phi cosine theta, and then, oh, I'm sorry, I miscopied that. I wrote a cosine theta there. That should definitely be an a cosine phi, not an a cosine theta. I just miscopied it as I transcribed it over here. Okay. So there are no thetas here, which means the partial of my z component with respect to theta is just 0. If I look at the partial of r with respect to phi, so that's going to be a cosine phi cosine theta, a cosine phi sine theta, and then negative a sine phi. So, if I want to take a look at the cross product of these two things, let's see, I think I've got space. Del r del theta crossed with del r del phi is going to be a symbolic determinant I, j, k. This is my second row, negative a sine phi sine theta, a sine phi cosine theta, 0. And then this is my last row, a cosine phi cosine theta, a cosine phi sine theta, negative a sine phi. Okay, so if I write out what I'm going to get here, for the i's, for the first component, I'm getting this 2 by 2 determinant. So it's going to be this diagonal product minus nothing. So I'm going to get negative a squared sine squared phi sine theta. For the j's, I'm getting the opposite of this 2 by 2, so I'll do it backwards. So I'm getting nothing minus this diagonal product. Now these two negatives will cancel, but I'm subtracting this, so I'm going to get negative a sine squared phi sine theta. And then for the k's, I'm sorry, that was a squared, wasn't it? Yes. Negative a squared. Sorry, I wrote a initially. For the k's, I'm going to get negative a squared sine phi cosine phi times sine squared theta that's this diagonal product, minus a squared sine phi cosine phi times cosine squared theta. Okay, now if I look at this last component here, notice that there I could factor out a negative a squared sine phi cosine phi because that appears in both terms. What it's multiplied by is sine squared theta plus cosine squared theta, but that's just 1. So all of this collapses down to just being negative a squared sine phi cosine phi. So I think what I'm going to do is just simplify that like so. So there's my cross product. Now I'm going to clear the board, but erase everything except that result, because what I need to do now is calculate the magnitude of that. Okay. So we're going to be looking at the magnitude of this cross product, and that's what we're going to need to integrate. Okay. Now, I kind of think this is a fun problem. I agree I'm a little bit weird. But what's going to happen when we calculate the magnitude is it's going to be long. And then we're going to simplify it, and simplify, and simplify. And it's going to get much, much smaller. And it's going to become something that is very reasonable to integrate. Now, at this point, this video has been going for a while. So I'm going to stop this video and pick up in the next video where we'll be calculating this. So let me just label. This was my del r del theta crossed with del r del phi. And in the next video, we will pick up with taking the magnitude of that and then integrating.